Qilin. So she will talk about recovery of water and critical mineral from oil and produced water. So please join me in welcoming her presentation.
I really appreciate that first presentation that gives you a very high level, introduction on where we are and brine mining. And I'm going to talk about a specific source of brine. Seawater, mining minerals from seawater is great and has both environmental benefits as well as financial benefits. And other industrial brines a lot of times make even more financial senses because we're dealing with much higher concentration of salt, as well as an industry that can afford to actually pay more to desalinate their wastewater. So as I mentioned earlier, I'm from the biggest oil and gas producing region in the US, in Texas. The produced water from oil and gas production has been and is increasingly becoming a very urgent challenge in the region and in many other oil and gas production locations around the world. This wastewater is produced when you pump oil and natural gas above the ground. So what comes up is a mixture of water, oil, and natural gas. And once you separate the three phases, you get a water that has very high concentration of hydrocarbon, but at the same time, in our region, extremely high salinity concentration. So in many places, the salt concentration can be over 200,000 milligram per liter. So many times higher than seawater. In the past, and still ongoing practice, is we take this wastewater and you dump them into deep injection wells. So those are wells that are several thousand feet in depth drilled into the ground. And in Texas, we have a lot of these disposal wells. In the past, that has always been the disposal location of this wastewater. But in the past couple of decades, there have been more and more frequent seismic activities caused by the disposal of produced water. So in a lot of places, disposal through this approach is no longer an option. But this water needs to go somewhere, right? At the same time, the oil and gas production usually happens in highly arid areas. In Western Texas, the farmers are running out of water, and so there is competition between the oil and gas industry and other water users for the freshwater resources, because the oil and gas industry not only produce a lot of wastewater, but they also require a large amount of water to produce oil and gas. So especially in places where they have to do hydraulic fracturing for production. So there you have a large water demand, but at the same time you have to dispose of a very large volume of wastewater. Then recovering water from that wastewater makes a perfect sense. The challenge again is the very high salinity and the large production volume. In the Permian Basin, where a large part of the Permian Basin is in Texas, the water to oil ratio is about 5:1. So in other words, every cubic meter or every barrel, that's what the oil people say, every barrel of water produced, you will produce 5 barrels of wastewater, and that's highly saline. So if there's a cost-effective way to recover the water from that wastewater and use it for beneficial purposes locally, then that would be of great financial benefits to the producers as well as to the local environment and local communities. Now, another very attractive reason for treating that water is that there are actually high concentration of minerals in that wastewater. There has been reported that lithium concentration as high as several hundred milligrams per liter is present in many locations in that produced water. So if we can recover water and these critical minerals, including lithium, then we're benefiting from both sources. Now, I'll talk about the recovering of fresh water from this highly saline wastewater first, right? So this is a plot we adopted, I think, from Qilin and Venice, one of their publications that looked at the desalination technology landscape, especially in the brine concentration and zero liquid discharge space. So if you look at the brine concentration, which is where I think the oil and gas companies is most interested, because for them, they wanted to reduce the volume they have to dispose of and extract fresh water, and whether or not they whether or not they can extract minerals from it is not as important, but of course that can negate their cost of the treatment, right? So that middle zone, the brine concentration range from 70,000 to up to 200, 250,000 ppm is the concentration, TDS concentration range of interest. So in that concentration range, the most common approach is obviously thermal evaporators, and that works well, and probably the only mature commercially available technologies out there for them to consider, but very, very energy intensive. Membrane-based technologies such as ultra-high pressure reverse osmosis would have been a lot more energy efficient, but right now the commercial reverse osmosis membranes cannot really provide or stand the extremely high pressure necessary to overcome the osmotic pressure of that hypersaline wastewater. So a lot of people work in the space of thermal membrane brine concentration, that's what we call them. One of the technology is membrane distillation, but still the technology is much more energy intensive than you would have achieved using reverse osmosis based technology. So the goal is to reduce the energy consumption of these thermal membrane brine concentration technologies, at the same time and make sure that they can even cover TDS range that's higher than what the current RO membrane technologies can. As I mentioned, a lot of people work in on membrane distillation technology. It has a lot of attractive features: low temperature, low pressure operation, and it allows you to potentially use low-grade heat energy and renewable energy, for example, solar energy, and it's less prone to fouling than reverse osmosis and relatively insensitive to TDS, but it has two fairly fatal deficiencies. One is that current MD technology has very low thermal efficiency, and very, very low water recovery can be achieved through this process. And the very low thermal efficiency is caused by several factors, temperature polarization being one well-known contributor. The diminishing temperature difference when you scale up the membrane module is a second very important reason, and of course thermal energy loss to the brine and the environment is a third contributor to that low thermal efficiency. If you look at this technology, through a thermodynamic point of view, this technology really cannot be a scalable technology, right? As I mentioned earlier, when you scale up the membrane, just like any heat exchanger, when you increase the membrane size, because the thermal energy input to the membrane unit is tied to the feed water flow rate. So when you increase the membrane size, you will experience diminishing average temperature driving force across the membrane module, and therefore diminishing average membrane permeate flux. At the same time, because the thermal energy input is tied to your feed water flow rate, right? So you can only heat your feed water up to 100 degrees Celsius under ambient pressure. So you're limited by how much thermal energy you can put per unit area of the membrane. So your maximum water recovery, even if we assume 100% energy efficiency, is less than 30%. So there's not a way to get around that. One approach that a lot of researchers have worked on is to decouple the thermal energy input from the feed water flow rate. So in this case, we can provide heat, not by heating the feed water, but provide the heat by heating the membrane surface. So interfacial heating or surface heated membrane distillation has attracted a lot of attention in the past decade or so. And there are several different approaches you can heat the membrane surface. You can use light with a photothermally active membrane coating. surface, or you can use dual heating. So electrically conducting membrane can conduct a current through the membrane surface, and the resistive heating can create a high temperature on the membrane surface. Conduction heating and induction heating are two other approaches that have been used. And if you compare these different surface heated membrane distillation method, and you can see that the photothermal approach, most of the time people try to use natural sunlight, can get you a very high energy efficiency. So compared to conventional MD, all of these surface heated membrane distillation processes have much higher energy efficiency. But if you try to use natural sunlight, because the very low intensity of sunlight, so on a global average, you have about 1 kilowatt per meter square of irradiated area in sunlight. So that very low light intensity results in fairly small permeate flux, even though you can get to a high energy efficiency. So the other surface heated methods has increasingly attracted more attention because you can provide much higher energy intensity and therefore achieving both. Let me get the laser. You can achieve both high flux and high energy efficiency at the same time. So if you look at this upper right region, where you can get a flux that's equivalent to what you can achieve with RO at much higher TPS, but also very high energy efficiency, more than 80% energy efficiency can be achieved if you manage the design of the membrane module properly. Now, any thermal methods is still, even with more than 80% thermal efficiency, is still going to be very energy intensive, right? Without any heat recovery and reuse of that thermal energy. So are there cheaper ways to recover the heat without using expensive heat exchangers? So one of the approaches is you can create a multi-effect membrane distillation module. In our study, we developed a multi-effect design using a spiral wound configuration that's very similar to what you see in a reverse osmosis membrane module. So the natural spiral wound structure provides multiple layers of membranes and allows you to recover the heat of condensation and use on the next layer of membrane to drive vapor evaporation again. And to overcome the limitation of the low thermal energy of natural sunlight, you can couple this technology with a parabolic solar trough concentrator. So that allows you to use concentrated sunlight on the membrane surface, and the concentrated sunlight increases the membrane permeate flux non-linearly because vapor pressure increases non-linearly with temperature. So you can drastically improve membrane permeate flux when you are using concentrating sunlight, also improving the thermal efficiency. But this means that you're going to have to need a very large land area to harvest enough sunlight to drive this still relatively slow process, right? So if you need a high throughput, so in the case of oil and gas produced water, high throughput is really necessary because they're producing huge amount of water every day. Solar membrane distillation is going to means that you're going to have to build massive desalination plant to trade the flow rate necessary. So another approach is to use electricity. So the dual heating approach can allow us to provide much higher thermal energy intensity into the system. But the challenge in dual heating in treating high salinity water is that most of the conductors are metal-based, and so in a hypersaline water, electrochemical corrosion is going to immediately damage your electrically conducting membrane. So in this case, we take advantage of a two-dimensional nanomaterial hexagonal boron nitride, which forms this beautiful two-dimensional nanoscaled layer. We can grow it on a commercial stainless steel mesh. So you can see here, this is a hexagonal boron nitride coated stainless steel mesh. It looks just the same as your typical stainless steel mesh, but it's protected by the HBN nano coating. The HBN nano coating has several very unique features. One is perfectly impermeable to water or any salt ion. So this isolates your electrical current from the surrounding salt solution. Secondly, it has extremely high thermal conductivity, and so any heat that's generated by the stainless steel mesh can very quickly be transferred to the surrounding brine solution very efficiently. Three, HBN is also a very strong material, has very strong mechanical properties, so it can resist scratching, scouring by particles as well. And so if you put this coating on a traditional membrane distillation membrane surface and use that as your heating element, and we also designed a spiral wound configuration where you have two pieces of membranes with the HBN coated stainless steel mesh sandwiched in between. Now with the heat can be used in both directions to drive vapor transport, and you can build a spiral wound configuration. And with that, you can actually achieve both high membrane flux as well as high thermal efficiency. So you can see here the spiral wound configuration almost doubled the energy efficiency of the flat sheet configuration using the exact same surface heating element, and it can handle TDS concentration. Here I'm going to show you on another plot. Up to 250,000 ppm of this. In this case, we tested in sodium chloride. So if you compare the throughput that can be generated by this approach with conventional reverse osmosis, right? So reverse osmosis has very high throughput because of the high permeate flux, but it's limited by the TDS concentration it can handle. The electrothermal membrane distillation can take that TDS range all the way up to 250,000, but produce membrane permeate flux that's very, very similar to what you can achieve in an RO system. And the HBN coating also has the additional advantage that is because it's super smooth, it's atomically smooth, and it also has a modulated polarity in its surface chemistry, so extremely resistant to scale formation. So here we compare scale formation on four different material surfaces: traditional polished titanium, and your smooth PVDF surface, graphene, which is another atomically smooth material, and HBN. HBN by far has the lowest scale formation potential. Now, with the few minutes I have left, I wanted to talk about the critical mineral materials in these produced water sources. So if you look at the main minerals in this produced water, of course, chloride is the most abundant ion in this produced water. Then the most abundant cation is sodium. But you also have significant concentration of lithium, cobalt, nickel, magnesium, and manganese. And if you look at their concentration together with the total amount, what we think make most sense are actually lithium and magnesium. So in 2017 alone, the lithium and magnesium content in this produced water in the US can meet 300% and 1800% of the US annual demand for these two elements. So if we can recover these elements cost effectively, then we can solve at least the dependency of US's dependency on lithium supply chain. So currently lithium is mined from either hard rock or brine sources. And the brine mining of lithium is very slow and not very environmentally friendly because it involves a lot of chemical precipitation and use of huge evaporation pond. So for environmental protection purposes, we wanted to avoid using this conventional lithium mining method, and so instead use direct lithium extraction, where you don't have to, well, you can skip the evaporation ponds. Now, a lot of the direct lithium extraction methods utilizes lithium selective adsorbent. So after pre-treatment to remove suspended solids and some scaling materials, and you would remove then calcium and magnesium, which interferes significantly with the lithium absorption on the selected media. Once the lithium is absorbed on the media, then you have to dissolve it using a huge amount of fresh water or acid. And the eluent oftentimes still contains significant concentration of calcium and magnesium, so you may have to do an additional step of calcium magnesium removal before you can get to a relatively clean lithium brine. So our goal is really to simplify this whole process. Right now, the cost for this production is not very high, but the equipment cost is extremely high since you have to do multiple steps of divalent cation removal and absorption and desorption and washing. So our goal is to replace this complex process with a very simple electrodialysis process, but with highly lithium selective membrane. The design of a lithium selective cation exchange membrane is challenging. You might have read the literature. There's a lot of effort trying to design lithium selective membranes, and it's relatively easy to develop a membrane that can select between lithium and calcium magnesium, but it's very challenging to design a membrane that can select between lithium and other monovalent cations. So what we did is we actually abandoned the traditional approach of making one layered cation exchange membrane. We use a design that's inspired by the structure of the reverse osmosis. So a thin film composite design, you may call it. In this design, we use 3 different layers of materials, each provide a unique function. In the middle layer, we use a porous ultrafiltration membrane to provide the mechanical support. And on one side of that membrane, we provide a cation exchange polymer. So the ionomer there will allow separation between cations and anions. And on the other side, we have a skin layer similar to what you see in a reverse osmosis. It's based on polyamide, but in that ultra-thin polyamide layer, we also include a lithium ion sieve. So the lithium ion sieve has extremely high selectivity between lithium and other cations. So basically, it only allows lithium to transport through. But the challenge here is how do we embed this material in there but prevent other cations to transport through the polymeric matrix, because that's going to reduce your selectivity, right? So that's why we choose interfacial polymerization process to minimize the thickness of the polymer skin layer and to minimize the gap between this ion safe nanoparticles. So those are just some model simulation to show you that the lithium titanium oxide nanoparticles we synthesized in the lab is extremely selective to lithium. So sodium cannot pass through this material at all, and you can increase the transport flux of lithium through this material by increasing the electrical potential. And then in order to make a defect-free skin layer so that you maintain the high selectivity of the lithium titanium oxide nanoparticles, we first modify the LTO nanoparticle with amine functional groups, and we allow it to react with TMC, so one of the monomers you use to make the polyamide skin layer in the RO membrane. So this way we're hoping that this complex of LTO and TMC can behave like a TMC in the interfacial polymerization process. And we show that, yes, indeed, it did behave like a TMC. We formed a very nice ultra-thin nanocomposite skin layer, which has a very high density of the LTO nanoparticles in that polyamide nanocomposite skin layer, and was able to maintain fairly high selectivity between lithium and other competing ions. So here you can see final results. We are able to maintain very high lithium to calcium and lithium to magnesium selectivity, so about 150, and a decent lithium to sodium selectivity, so about 13, 14. Still not as high as LTO nanoparticle because we haven't optimized the polyamide matrix, but this shows the promise of such a interfacial polymerization approach, and also the thin film composite structure that allow us to independently tune the functions of each of the three layers, allow us to make a membrane that can allow precise mineral recovery from this complex wastewater. So, and this work was done by a large group of people, so I wanted to give them credit and thank them for their contribution in the past few years. Thank you.
Thank you, Qilin. So one burning question. Anybody for this medium and recovery from the oil and gas produced water? Anybody? Otherwise,